whole chunk of data, you can say, just give me the exact number of samples I need to complete the tag to get the rest of the tag signal. What we did is actually drop the latency of, our first one had 70 milliseconds worth of latency. And it was a pretty naive implementation. But we ended up driving that all the way down to 300 microseconds. So we can now talk to standard RFID tags as well as the WISP. So there's just some this is the most high-level performance of our reader. So the first thing to realize is that read rate of an RFID reader means almost nothing. We've already seen it where these sample rates and numbers are all over because there's so many parameters that factor into that. So if you look at the bottom line, this is actually a commercial reader where we scaled it down so it's putting out the same output power. What you can see is that it reads all the way out to 8 feet and then it can't read any tags past that distance. And if you pop up a line to the kind of thicker dash line, that's a performance of our software-defined reader. So you can see that it drops off. It has a higher read rate because we're sending queries more quickly, so we end up reading faster. But you can see is that we have about 6 feet, and after 6 feet, we can't read any tags. So what we wanted to see was whether that was a problem with our signal processing, so maybe we actually had some more headroom that we could capture if we did something smarter, or if it was because the tag wasn't powering up. And what we found is if we moved the receive antenna out right next to the tag, we could read the tag out to 8 feet also. So what happened was beyond 8 feet, the tag's not even powering up. So we actually get about 75% of the overall read range. So in conclusion, we actually have a flexible Gen 2 reader. And when you're using this with a WISP, you now can actually, from the PHY layer and the MAC layer all the way on up, build totally different protocols. So it really opens up what I think is a lot of the potential of the WISP, because now you can control both ends of the equation. And if you want to look at the paper or actually the source code, if you have a USRP, you can just start running this reader. It's at my website. Actually, it's not on the website because we don't have Wi-Fi access here. My plan was to upload it today, so it's not there. It'll be there tomorrow. That's it. Any questions?
All right. Well, thank you, first of all. So, I'll start off. I had 2 questions. So I can see the benefit of a software radio reader for reading regular tags, but if we've got a software radio for an RFID reader and we have a software tag, why are we using EPC Gen 2 in the first place? Why not just use those two to build a protocol that's better suited to the kind of workloads we'd expect on WISPs?
Oh yeah. I mean, that's my research plan.
Excellent.
In a nutshell.
Let me know if you need a PhD thesis outside reader. Okay.
Right.
Second question. A lot of your things on latencies. Well, what about competing software radios like Sora at Microsoft Research Asia?
Right.
Where it's a PCI card, so they cut down on a lot of the.
Yeah.
latency.
I mean, one of the nice things about this is it's cheap, it's easy, accessible. You buy it. Sora boards, they aren't actually available as far as I know. The Warp boards, which there's something came out of Rice University, again, really low latency. They'll set you back 20 grand. I mean, this is kind of the poor man's software radio, which I like because it means it's accessible to everybody, basically.
Okay. Other questions?
Okay, we see that we have a standard EPC2, right, at present. Previously there was EPC1 and then it upgraded EPC2. So every time this gets updated, we have to reconfigure the readers. So I was just thinking, how costly is this operation? Like, probably if tomorrow I have to reconfigure a reader, like, should I go to the actual code and do it myself, or is there a very streamlined process of doing it when I have a text file and just change my tags and length of the field?
So using something like this, or using, for example, an Impinj reader? So I presented, this is kind of a custom-built software. The hardware is not custom-built, but it's just my own software. So it's mostly a research and development platform. I mean, this wouldn't actually be used by Walmart. I think companies like Impinj probably have some of their software can be field upgradable. So maybe you can actually go to Gen 3. But you would actually, for this, if you wanted to use my reader, you'd have to rewrite some of that software.
Hi. My question is actually just kind of a background regarding the test setup you used for the USB and such. I just want to confirm you were using standard x86 hardware and Linux 2.6 or 2.4 kernel?
Yeah. I mean, one key is you have to use a real-time kernel.
Right, yeah.
It was just a 2.6 real-time kernel. There was no magic. I mean,
okay.
It was I can run it on my laptop as long as you run the right kernel, and that's documented in the software. Is the kernel versions that I have working. It's just Ubuntu. It's nothing special.
And I guess the quick follow-on to that then is, based on this work, do you see any, if you had to improve the performance further, would you be focusing more on the implementation of the universal radio end or the Linux USB stack?
To drop the latency more?
Yes.
So I think I have it pretty close to the theoretical minimum given the USB bus. But there is the USRP2 now, which uses GigE instead of USB. But the problem is it only takes one daughter board instead of two. So now there's a question of, is there any way to separate my transmit chain from my receive chain? So it's not, the USRP2 has much lower latency, but I'm not sure that we can actually get it to do this at all, given the RF. Sure.
All right. Thank you. Thank you again. So our second talk, Ben Ransford, is going to talk about some of the challenges he went through in using the WISP. Getting echo, I think. And I can't remember how many years of the learning curve it was for you, but I hope this, again, will save people in the audience from that kind of a delay. So, reducing latency. Go ahead.
Hello? Okay, guess so. That's somebody telling me yes. Right, so my talk is about challenges to WISP application designers. We've been working with WISP since the early first revision prototypes back in, I guess, 2007. So we've accumulated quite a bit of empirical experience with trying to actually do things on the WISP. Before I start, I want to thank Intel, of course, for planting all these seeds, and I want to thank, I counted just earlier, the NSF is actually funding my standing here in 3 different ways, by at least 3 unique channels, so thanks to NSF. Right, so where to start? I'm one of Kevin's advisees. We work nominally in security. This WISP and radio stuff has sort of crept in from the boundaries and now consumes graduate students. Right. So where have we gone? Before 2007, before we started doing all the WISP stuff, there was a lot of RFID security work that came out of our lab. Somebody mentioned the credit card work earlier. There's a photo you can't really see too well of Kevin and another student. That was from Financial Crypto 07. Starting around 2007, we actually started getting our hands on these WISP prototypes. And there was a paper at RFID Sec 07 about doing crypto, doing RC5 on the WISP. There was another thing that we saw a slide about before about gathering random number information from the SRAM cells. In 2008, we had this idea that we could use the WISP as a gatekeeper between 2 other devices, and I'll talk about that in a minute. And we also made a paper about using execution checkpointing on the WISP, which I'll also talk about later. And then this year we've been working quite a bit on secure remote storage for the WISP, and also the stuff that Shane talked about before about Solar, or that Kevin talked about. There's also a bunch of other projects that I couldn't fit on that slide. There's Concrete, so we're trying to sense what's going on inside concrete after it's cured. There's this Franken-WISP thing that Shane talked about briefly. This is my artist's rendition because I didn't have a good photo. But essentially, it's a WISP tethered to a moat. And we don't have to necessarily use an oscilloscope to tell what's going on the WISP. In fact, we can just use the ADC that's on the moat to do very fast reads and get pretty high resolution, a pretty high resolution picture of like the WISP's capacitor voltage. So great. So what lessons have we learned in approximately 2 years? And I want to be fair to us. This wasn't like 24 months of staring at source code and trying to solder things onto the WISP. Like I said, we work in security, so this was mostly sort of driven by learning on demand things that we needed to get what we wanted done. So I'll just jump right in with lesson number 1, which is to scale your expectations. That could mean a lot of different things, but for me it means scale down my expectations of what a WISP can do, or what sorts of what a device like this could do in this model.